Welcome, myself Gksr. I'm from Department Electronics and Communication Engineering. Today I'm going to present digital communication subject of subject code having 18EC61. The topic for today's presentation is gram skimmed orthogonalization procedure. It was presented by me, Gksr. Moving to the next slide, that gram skimmed orthogonalization procedure. Consider set of m energy signals s1 of t, s2 of t, and so on as m of t, as we are considering m energy signals. Thus, gram skimmed orthogonalization allows us to determine a set of n orthogonal functions such that each si of t can be expressed as a linear combination of n orthogonal effects. Let phi 1 of t, phi 2 of t, and so on, phi n of t are orthogonal functions that has to be determined. We know that si of t is equal to summation j equal to 1 to n si j into phi j of t. These are all some basic formulas that need to remember. S1 of t is equal to S1 of S11 into phi 1 of t plus S12 into phi 2 of t plus and so on, S1n into phi n of t. This is equation 1. Consider these as equation 1. S2, as these equations are reused later in the further derivations, that's why we are considering this as equation 1. S2 of t is equal to S21 into phi 1 of t, S22 plus S22 into phi 2 of t plus and so on, S2n into phi n of t, which is equation number 2. Yes, and so on, S3 of t, S3, S4 of t, and so on, up to as we considered m functions, so that Sm of t is equal to Sm1 into phi 1 of t plus Sm2 into phi 2 of t plus and so on, Smn into phi n of t, which is equation m. We know that integration 0 to t phi I of t into phi j of t dt is equal to 1 if I equal to j, or else if I is not equal to j, the value of this integration is 0. Therefore, finally, to start compiling orthogonal functions, consider the following steps. There are two steps involved in this process. Step 1 from equation, step 1 is shown here. From the step 1, we can prove that phi 1 of t is equal to s1 of t divided by s11 of t. Move to the next slide. By squaring on both sides and integrate from 0 to 1, integration 0 to t phi 1 square of t dt is equal to integration 0 to t s1 square of t by s11 square of dt. From this, we can prove that if phi 1 of t is equal to s1 of t by square root t1. From this derivation, we can prove that phi 1 of t is equal to s1 of t by square root t1. And also from the step 1, we can prove that the same, that phi 1 of t is equal to s1 of t by s11. Yeah, hope you understood the step 1. Moving on to the step 2, as we consider the equations for above, set all coefficients except s21 s22 to 0. S2 of t is equal to s21 into phi 1 of t plus s22 into phi 2 of t, which is equation a. Consider these as equations a, b, c, d, and so on, as we consider the numbers in the step 1. From this step, we can prove that s21 is equal to integration 0 to s2 of t phi 1 of t. This can be considered as equation C. If S21 is known, then the equation A can be written as the given. Moving to the next slide. The process continues. The derivation happens step by step. From those, we can prove that phi 2 of t is equal to 1 by s22 into s2 of t minus s21 into s1 of t by s11, since phi1 of t is equal to s1 of t by s11. uh, in this fashion we can determine that function we can determine that other order orthogonal functional coefficients. We can generate the equation as gi of t is equal to si of t minus summation j equal to 1 to I minus 1 Sij phi j of t, where Sij equal to integration 0 to t Si of t phi j of t dt. From this derivation we can prove this equation. We can for further mm, analysis, we can for further clarification we can take one example too. uh, it is given in here in this slide. Consider the signals s1 of t, s2 of t, s3 of t, and s4 of t. We are considering four signals as shown in the PPT presentation. We wish to use the Gram-Schmidt orthogonalization procedure to find the orthogonal biases for this set of signals. As we know that the process includes two steps. Step one is, we know that the energy of the signal s1 of t is equal to is e1 of t, which is equal to integration 0 to t s1 square of t dt. This is the energy of the signal. For the From the derivation, we can prove that energy of s1 of t is t by 3. The first basis function phi1 of t is therefore phi1 of t. We can prove that we proved in the derivation that phi1 of t is equal to s1 of t by square root of e1. The same formula is used here, so that phi1 of t is equal to square root of 3 by 4 under the limits of 0 to t, that t by 3. Otherwise it will become 0, which the intervals does not lie at 0 to t by 3. The value is 0. Into the next slide. We are proceeding to the next step 2, evaluating the projection of s2 of t and onto phi1 of t. Find that s21 is equal to integration 0 to 2 s2 of t phi1 of t dt. These are all formulas which we have derived before. S21 is equal to square root of 3 by t, from the derivation of the derivation from the presentation. The energy of the signal s2 of t is equal to the energy of the signal uh, e2, which is equal to integration 0 to t s2 square of t. This we have derived in the previous derivation of step 1. E2 of E2 is equal to 2t by 3 from the further derivation of the formula. Moving on to the next slide, the second basis function phi2 of t is therefore phi2 of t is equal to s2 of t minus s21 phi1 of t by square root of e2 square minus s21 square. This can be written as phi2 of t is equal to square root of 3 by t under limits t by 3 to 3 by t. If the limit does if the value does not lie between t by 3 and 2t by 3, the value will be 0. The next step, we are entering to the next step 3, evaluating the projection of s3 of t onto phi1 of t. S31 is equal to integration 0 to t s3 of t phi1 of t dt. From the simplification, s31 is equal to 0. S32 will be equal to square root of 3 by t. Therefore, the corresponding value of the intermediate function gi of t with I equal to 3 is therefore s3 of t is equal to 1 if the t lies between 2t by 3 and 1. If the value of t lies between anywhere else other than 2t by 3, other than in between 2 3 by 3 and 1, it will be 0. Hence the third base is function phi 3 of t is equal to g3 of t into square root of 0 to t g3 square of t dt. Move to the next slide. The orthogonal process is now complete with this um, steps. The three basic functions phi 1 of t, phi 2 of 3, phi 3 of 3 from an orthogonal set shown in figure. In this example, we have m equal to 4 and n equal to 3, which means that the four signals s1 of 3, t, s2 of t, s3 of t, and s4 of t described in figure do not form a linearity independent set. This is readily confirmed by nothing that s4 of t is equal to s1 of t plus s3 of t. Moreover, we note that any of these four signals can be expressed as a linear combination of three basis functions, which is the essence of Graham's schematic orthogonalization process. I hope you understood the concept. I'm feeling so grateful presenting in front of you. Thank you for listening to the class, and then bye bye.